Hi guys, this is your notes presentation on neutralization reactions. Um, these are going to be a little interesting to comprehend because we haven't talked about ionic, net ionic, or complete ionic reactions yet, but just bear with me. They're not that bad. You just have to look at molecular equations a little bit differently than you have in the past. So the first thing to know is that acid plus base is a neutralization reaction because the two are going to neutralize one another. And now you've all probably seen a neutralization reaction before. You definitely all have had neutralization reactions happening in your body this entire time you've been alive, but you may not have thought a lot about them before. But the video that I wanted you to watch today as you were doing this assignment associated with the notes presentation is a neutralization reaction. That's what a baking soda volcano is. Um, if the acid is stronger in this neutralization reaction than the base, then the overall solution at the end will be acidic. If the acid is weaker and the base is stronger, then the overall solution that you get after the reaction happens is basic. So here's a generic example of an acid reacting with a base. That is always going to form salt and water. And I don't mean necessarily table salt, though sometimes it is table salt. But in this case, we have our acid and our base reacting to form magnesium chloride and water. And magnesium chloride is a salt. Remember, another term for an ionic compound is a salt. So I don't, again, mean necessarily table salt, but any salt. So strength is going to determine whether or not an acid or a base is going to ionize. So if it is a strong acid or a strong base, if you dump that into water, it's going to ionize immediately. Meaning, like, if you have, for example, from this last slide, if you had solid hydrochloric acid, like here, if you dumped that solid hydrochloric acid into water, it would immediately split up into H plus ions and Cl minus ions. And that's what I mean by strong acids and bases will ionize, whereas weak ones will not. So if you had a weak base, something that's a base, but it's not necessarily a super strong base, or something that's an acid, but not necessarily a strong acid, you're not going to get as much ionization, as much breaking apart in water as you would with a strong acid or a strong base. Things that you should be aware of going forward is that anything that is considered a salt will always ionize in water. So ionic compounds are generally going to ionize in water because they are salts. Water, on the other hand, is not going to ionize, which shouldn't surprise you because water sitting by itself, like pure water, is not going to all of a sudden break up into H plus ions and OH minus ions. It's just going to sit and be water. So to ionize, again, is to break apart into ions. So if you have the MgCl2 salt, magnesium chloride, if you threw that in water, it would immediately break up into Mg2 plus and 2Cl minus. So when you're doing this, because I am going to ask you to write ionic equations later, you do have to remember that when you start with a compound and you're going towards the ions, the swap and drop that was originally done to get this compound, that goes in reverse. So now that 2 is going to float back up, and Mg2 plus, the implied 1 here, is going to float back up into the right and become Cl minus 1. And that's just something that you should be aware of already, given that I had you write compounds already. You already should know how to do the reverse swap and drop. Or you could have just known that these two things would break up and looked on the periodic table to figure out what their ionic charge would be. So what is a net ionic equation? Well, that's an equation that shows only the ions that are directly involved in any particular chemical reaction. So up until this point, we haven't really looked at chemical reactions other than regular molecular chemical reactions. So like, for example, down here on the bottom, you have your NaCl, your regular table salt that's aqueous. You have your silver nitrate over there that's in aqueous form. Those things are reacting to produce silver chloride and sodium nitrate over here. But you'll notice that in this reaction over on the right, the silver chloride dropped out of solution. It became a precipitate. So that is no longer in solution. It's a solid that's non-soluble that's resting on the bottom of this beaker over here. And so that's why we give it the little subscript of S to represent that solid form. So to take a closer look at what's going on in this equation, we have the molecular equation, the NaCl, AgNO3, NaNO3, and AgCl over here. So this is what you're used to looking at, this type of equation. We can also write it like this, though, because this AQ here with the reactants means that that reaction is taking place in water, which was obvious to us in the picture that I provided you back here because you saw that it was happening in solution in this beaker. So what happens to salts when they are in solution? They break up. So really what's happening in water is you have sodium ions, you have chlorine ions, you have silver ions, and you have nitrate ions all floating around in solution. Once the reaction takes place on the other side, your sodium and your nitrate ions are still floating around in solution, but your silver chloride has dropped out of solution and is on the bottom. So really, the only reaction that took place here is the reaction between the silver, the chlorine, because really nothing happened between the sodium and the nitrate other than the two compounds broke apart over here. Nothing else happened with those. You see, they're still in solution before and after. The only actual bonding that took place was between silver and chlorine. So that's what happens when we write a net ionic equation. What you first have to do is you take your molecular equation over there and you write all of it out as a complete ionic equation. So after you do that, after you have your complete ionic equation, which is all the ions that are represented by these molecules up there, you start crossing stuff out. And the way you do that is you look on the product side and anything that's still aqueous, you're going to cross that out and then go back to the reactant side and cross that out. You go back to the product side, that one's aqueous too. Cross that out. You're going to go ahead and cross that out over on the left side. And now all of a sudden, all you're left with is chlorine, silver, and the AgCl that's here as a solid on the right. And that's what we do to write our net ionic equation. You just take whatever is left and make an ionic equation out of it. Okay? So, oops, let me erase all this. You may or may not be asking yourselves right now, how do I know? How do I know if it's solid? How do I know if it's liquid? How do I know? How do I know? How do I know? Well, sometimes the molecular equation will be given to you and that information is given. And that's really easy because if it says solid, then it's a solid. But if you had to figure out if something was solid, you would consult your solubility rules, which we already learned about. You should know that all nitrates are soluble in water. Acetates are soluble generally, except for when they're bonded to silver. Chlorines, bromines, iodines, we have sulfates, carbonates, phosphates, hydroxides, etc. And you should be familiar enough with these, or at least have the ability to look it up to figure out if something is soluble or if it is not. So here's another example, but this example is more in line with something that we're going to see because this is an acid reacting with a base. So In this equation, we have hydrochloric acid reacting with sodium hydroxide to produce sodium chloride and water. So here's something to keep in mind. Sodium chloride is a salt. I told you earlier, all salts are always soluble. HCl, that is a strong acid, which is going to ionize in solution. Sodium hydroxide is a strong base, which is going to ionize in solution. But let's pretend that you don't know that information. You have no idea if hydrochloric acid is a strong acid or not. You have no idea if sodium hydroxide is a strong base or not, which at this point you probably don't know off the top of your head. So let's go back to our solubility rules and let's check. We look at our chlorides and we go, okay, well, I want to know, is that soluble in water? Well, all chlorides are soluble except if they're bonded to silver, lead, or mercury. Hydrogen is not any of those three, so guess what? HCl is soluble in water, so those things will ionize. Sodium hydroxide, let's look. All hydroxides are insoluble except when it's bonded to sodium or potassium. So looking at the equation, that's bonded to sodium. So this is soluble as well. So we know that these things would ionize in water, and therefore in our complete ionic equation, or in solution right here, we have our hydrogen ion plus our chlorine ion plus our sodium ion plus our hydroxide ion on the left. And on the right, salts are soluble. So we have our sodium ion again and our chlorine ion here, but water does not ionize. Water does not break apart in water. That wouldn't make any sense. So now water, essentially, some things happened there to create water, because over here you did not originally have water, unless you're talking about the water that this reaction took place in the first place. But what I'm telling you is more water was created over on the right. So when you write your net ionic and you're crossing stuff out, once again, anything that you know that is still in solution, you're crossing out. So you should cross out your sodium and you should cross out your chlorine. And you're left with hydrogen plus hydroxide yields water, which is exactly what our net ionic is down here. H plus OH minus yields water. Okay? Now let me erase really quickly and move on. So, strong acid and strong base reactions are going to form a neutral solution, which makes sense because if one thing is neutralizing the other, then all you're left with is water. If, on the other hand, you have a strong acid with a weak base, you're going to end up with a solution that is acidic, actually. So let's go through this. So here we have hydrochloric acid and magnesium hydroxide yielding magnesium chloride and water. So on this side, I'm going to start with what we end up with on the right. Magnesium chloride, that's a salt. That is an ionic compound, therefore it is a salt. So we know that MgCl2 is still aqueous on this side, and I'm going to write that AQ right over there just to remind us. We figured out last time that HCl ionizes in water, but if you weren't sure, you could still go and check the solubility chart. So that is going to give us our H plus and our Cl minus over here. Now, this, on the other hand, our MgOH2, this does not ionize completely in water. And you know that because you're going to go back to the solubility rules and you're going to look at hydroxides and you're going to remember that hydroxides are generally insoluble except when they're bonded to sodium or potassium. Magnesium is not sodium or potassium. So this, in our complete ionic equation, is going to remain a molecule. And now on the right side, we have our Mg2 plus, our 2Cl minus, and we have water because again, water does not ionize. So when you're crossing stuff out, you're only crossing out what is aqueous on both sides. So in this case, we're crossing out our magnesium on this side. Sorry, we're not crossing out magnesium. I don't know why I did that. Hold, please. Sorry, my apologies. We are going to instead cross out chlorine because it is in an ion form on both sides. We can't cross out magnesium, even though I was trying to do it anyway because I had a derp moment, because it is not ionic on both sides. We have magnesium in its ion form here, but we do not have it in its ion form over there. So therefore, magnesium needs to stay. So really all that we've crossed out here is the chlorine. And in this case, we have our H plus on this side, our MgOH2 or our magnesium hydroxide. We have magnesium in its ionic form on the right and water. And since we could only cross out the chlorines. And that tells us, since our net ionic equation contains H plus ions, that tells us that our solution overall is slightly acidic because we have this H plus ion that did not get dealt with all the way over there. All right, so let's erase some stuff. There we go, moving on. Like I said before, you're left with extra hydrogen ions, therefore that solution is acidic. With our weak acid and our strong base, on the other hand, you're going to be left with extra hydroxides. So let's go through this example real quick. We have H2S, we have CaOH2, we have CaS, and 2H2O. So in this case, what we have here is H2S, which isn't great at ionizing in water. It does a little bit. And we have calcium hydroxide, which actually does, because calcium is one of those exceptions for hydroxide in terms of solubility. And then on the right side, we have our CaS, which is a salt, and therefore it's going to ionize in solution and water. So when we're crossing stuff out, we have our calcium that can go away because it is ionic on both sides. And that's all that we can cross out. So we're left with our H2S, our 2OH minus, yielding our S2 minus and 2 waters on the right. Okay. Now, in this case, there were leftover hydroxides, which made that solution basic. So there is one thing that I would very much like to draw your attention to, which is this solubility table. So this is only one of the resources that you could theoretically consult here. I honestly would recommend, instead of looking up this solubility table, which you definitely could, and I'm not telling you you shouldn't, but there are other tables of strong acids and strong bases versus weak acids and weak bases. And honestly, you guys, I think it would be a lot more beneficial for you to be looking up a strong acid versus weak acid table or a strong base versus a weak base table. And the reason that I'm telling you that is so that you don't have to look at that molecule and figure out, is it going to dissolve in water? Is it not going to dissolve in water? Whatever. You could just look at that table and go, hey, it's a strong acid. It's going to dissolve in water. Or, hey, it's a weak acid. It's not really going to dissolve very well in water. So I'm just saying it might be beneficial for you. If you wanted to look at both, you can do that. If you're more comfortable with this table and think that you can use it with accuracy, that's fine too. But at least look it up, see what those tables are all about. They're very easy to navigate if you would like that. Anyway, I am going to be posting a video of a couple of practice problems for writing net ionic equations for the worksheets that I have given you. Stay safe, have a good day, and try not to get coronavirus, yeah?